Look up at the night sky. Thousands of stars twinkle back at you, each one a burning sphere of gas, light years away. They've captivated humanity for millennia. Their mysteries run deep. Stars are more than just points of light. They are the building blocks of galaxies. They create the elements essential for life. Understanding stars is understanding the universe and our place in it. Their life cycle is a story of immense power. It's a tale of creation and destruction. It's a journey through billions of years, and it all starts with a simple cloud of gas and dust. Stars are born in nebulae, vast clouds of gas and dust scattered across the universe. Gravity is the driving force. It pulls these particles together. Slowly, the cloud collapses under its own weight. As it shrinks, the center heats up. This dense, hot core is called a protostar. Think of it as a star in its infancy. It's not quite a star yet, but it's getting there. This process takes millions of years. It's a slow, gravitational dance. But eventually, the pressure and heat at the core become unbearable. And that's when things get really interesting, the birth of a star. The protostar is a hotbed of activity. Gravity continues to pull in material. The core gets denser and hotter. Temperatures reach millions of degrees. Atoms are no longer independent. They're forced to fuse together. This is nuclear fusion, the engine of all stars. Hydrogen atoms combine to form helium, releasing tremendous energy in the process. This energy pushes outward, counteracting gravity's inward pull. The protostar stabilizes. It's no longer collapsing. It's shining with its own light. A star is born. Our sun is a main sequence star. It's in the prime of its life. It will stay this way for billions of years, steadily fusing hydrogen into helium in its core. This is the longest stage of a star's life. The main sequence isn't a one-size-fits-all stage. Some stars are massive and hot, burning brightly with a bluish-white light. Others are smaller and cooler, emitting a dimmer red glow. Our sun falls somewhere in between. No matter their size, all main sequence stars share a common fate. Eventually their hydrogen fuel begins to run out, and that's when the next chapter of their story begins. A star's life is a constant battle between gravity and energy. For billions of years they exist in equilibrium, but when hydrogen runs low, the balance shifts, fusion slows down, the outward pressure decreases. Gravity, always present, takes over. The core contracts, becoming denser and hotter than ever before. This intense heat triggers a new round of fusion in the outer layers. The star is fighting for survival, but it's a losing battle. What happens next depends on the star's mass. The universe has two very different endings in store. A tale of two stars, small versus massive. Smaller stars like our sun take a gentler path. They transform into red giants, their outer layers expanding outward. They engulf nearby planets, leaving behind a glowing stellar ember. Massive stars, on the other hand, go out with a bang. They become supergiants, even larger and brighter than red giants. Their end is a spectacular explosion, a supernova that can outshine an entire galaxy. Both endings have profound implications for the universe. They scatter newly formed elements into space. These elements become the building blocks for new stars, planets, and even life itself. Red giants and white dwarfs, the twilight of average stars. As a small star runs out of hydrogen, it begins to fuse helium. This marks a significant transition in the star's life cycle. The core contracts under gravity, heating up to temperatures high enough to ignite helium fusion. This process releases a tremendous amount of energy, causing the outer layers of the star to expand. This causes the star to expand dramatically, becoming a red giant. The star's outer layers swell to many times its original size, and its surface cools, giving it a reddish hue. This phase can last for hundreds of millions of years, during which the star loses a significant amount of its mass through stellar winds. Our sun will eventually expand past Earth's orbit, engulfing the inner planets. This dramatic transformation will have profound effects on the solar system, potentially vaporizing any remaining life on Earth and altering the orbits of the outer planets. The sun's expansion into a red giant is a natural part of its evolution, driven by the inexorable forces of nuclear fusion and gravity. Eventually, even the helium runs out. When the star exhausts its helium fuel, it can no longer sustain nuclear fusion in its core. The core contracts further, and the outer layers are ejected into space. This marks the end of the red giant phase and the beginning of the star's final transformation. The outer layers of the red giant drift away, forming a beautiful planetary nebula. These glowing shells of ionized gas are illuminated by the hot core of the star, creating stunning cosmic displays. Planetary nebulae are short-lived, lasting only a few tens of thousands of years before dispersing into the interstellar medium. The core, now incredibly dense and hot, becomes a white dwarf. This remnant is composed mostly of carbon and oxygen, and it is incredibly compact, with a mass comparable to that of the Sun, but a volume similar to that of Earth. The white dwarf is no longer undergoing nuclear fusion, but it remains extremely hot, glowing brightly in the visible and ultraviolet spectra. White dwarfs are incredibly small, about the size of Earth. Despite their diminutive size, they are incredibly dense, with a single teaspoon of white dwarf material weighing tons. This density is a result of the electron degeneracy pressure that supports the white dwarf against further gravitational collapse. They no longer produce energy through fusion. Without a source of energy, white dwarfs gradually cool and fade over time. They radiate their residual heat into space, slowly losing their luminosity. They slowly cool over billions of years, eventually fading into darkness. This final stage marks the end of the star's life cycle, as it becomes a cold, dark, and inert object known as a black dwarf. However, the universe is not old enough for any black dwarfs to exist yet, as the cooling process takes longer than the current age of the universe. Supernova, the spectacular demise of giants. Massive stars live fast and die young. These colossal celestial bodies, often many times the size of our Sun, have a relatively short but incredibly dynamic lifespan. They are born in vast clouds of gas and dust known as stellar nurseries, where gravity pulls the material together to form a protostar. They burn through their fuel much faster than their smaller counterparts. This rapid consumption of hydrogen fuel leads to a shorter lifespan, often just a few million years compared to the billions of years for smaller stars. As they burn, they shine with an intense brightness, illuminating the cosmos. Their core becomes a cosmic onion, with layers of progressively heavier elements fusing together. This process, known as nucleosynthesis, creates elements like helium, carbon, oxygen, and eventually iron. Each layer represents a different stage of fusion, with the heaviest elements forming in the core. Eventually, the core collapses under its own gravity. When the fusion process reaches iron, the star can no longer sustain the energy needed to counteract the gravitational forces. The core implodes, causing a catastrophic collapse that happens in a matter of seconds. This triggers a shock wave that rips the star apart in a massive explosion, a supernova. The outer layers of the star are blasted into space, creating a spectacular light show that can be seen across vast distances. The energy released in a supernova is so immense that it can briefly outshine an entire galaxy. This brilliant display is not just a visual spectacle, it plays a crucial role in the cosmic ecosystem. The explosion disperses elements throughout the universe, enriching the interstellar medium with heavy elements. Supernova are essential for life as we know it. The heavy elements created in these explosions, such as carbon, oxygen, and nitrogen, are the building blocks of life. Without supernovae, the universe would lack the necessary ingredients for planets and ultimately for life to develop. They create and disperse heavy elements like gold and platinum. These precious metals are formed in the extreme conditions of a supernova and are scattered across the cosmos, eventually becoming part of new star systems and planets. These elements are scattered throughout the universe, seeding the formation of new stars and planets. The remnants of a supernova can trigger the birth of new stars, continuing the cycle of stellar evolution. In this way, the death of a massive star leads to new beginnings, contributing to the ever-changing tapestry of the universe. Stellar remnants, black holes, neutron stars, and the circle of life. In the vast expanse of the universe, stars are born, live out their lives, and eventually die. But their death is not the end. Instead, it marks the beginning of a new chapter in the cosmic story. After a supernova, the core of the star is left behind. This explosive event is one of the most powerful forces in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. The outer layers of the star are blasted into space, creating stunning nebulae that can be seen across vast distances. If the core is massive enough, it collapses into a black hole, an object so dense that nothing, not even light, can escape its gravitational pull. Black holes are mysterious and fascinating objects. They warp space and time around them, creating gravitational waves that ripple through the cosmos. Scientists are still uncovering the secrets of these enigmatic entities, using advanced telescopes and simulations to peer into their depths. If the core is less massive, it forms a neutron star, an incredibly dense object composed mostly of neutrons. Neutron stars are the remnants of supernova explosions, and they are among the densest objects in the universe. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are fascinating objects, spinning rapidly and emitting powerful beams of radiation. These beams can be detected as pulsars, which are like cosmic lighthouses, sending out regular pulses of radio waves, X-rays, and even gamma rays. The study of neutron stars helps scientists understand the extreme conditions of matter and the fundamental forces of nature. The death of a star, whether quiet or explosive, isn't the end. The remnants of these stellar giants continue to play a crucial role in the universe. The elements created in the heart of the star are scattered into space, enriching the interstellar medium with heavy elements like carbon, oxygen, and iron. The material ejected into space eventually becomes part of new stars and planets, continuing the cycle of stellar life and death. This cosmic recycling process ensures that the universe remains dynamic and ever-changing. New stars are born from the ashes of the old, and the cycle of life and death continues, driving the evolution of galaxies and the cosmos itself. Thank you for joining us on this journey through the life and death of stars. From their spectacular births in nebulae to their dramatic ends as black holes and neutron stars, the cosmos never ceases to amaze and inspire. If you enjoyed this video, don't forget to like, share, and subscribe for more fascinating insights into the universe. Until next time, keep looking up at the stars and wondering about the mysteries of the cosmos.